All right, hello everyone, and welcome back to this week's live stream for Physics 8A. First of all, apologies. I know the live stream is late. I actually got super sick, and being sick doesn't really prevent me from doing physics, but it did prevent me from talking without coughing and sounding super congested, which would have been a terrible live stream for anyone to listen to. So, apologies it's late. I know some of you like to catch up over the weekend, and we're hoping that it would be posted before then, but I'm catching up now and should be on track moving forward. So try to post the live stream every Tuesday so that you have, at the beginning of the week, you have what you need for that week um, to cover the material and the topics of that week. So this week is going to be the third live stream that I'm catching up on. This time it's basically it's Newton's laws. So it's a continuation of kinematics in the sense that kinematics so far have been about why or how rather an object moves and not why it moves one way or the other. In other words, acceleration was either given or you knew it was gravity because of free fall, but you couldn't find the acceleration on your own. You couldn't be told, a certain number of forces, for example, are exerted on this object. What's the acceleration? And the goal of at least Newton's second law is to give you those tools so that you can then take the acceleration and plug it into kinematics if need be. So there's a lot to say about Newton's laws. Again, my goal is not to do a lecture when I do these live streams. It's really to just summarize the important topics of the week and perhaps try to organize them in a way that gives you a bit more clarity. Which sometimes you don't get from lecture because lecture can be very linear sometimes, which is fine. It makes sense to present the material for the first time in that way. But then it's nice to kind of zoom out and have a look at how this fits into what we've been learning about position, velocity, and acceleration. So I'm going to start with that. In fact, that's not even true. I'm going to start with a good question that I got this week, a lot about projectile motion. So when I get questions and I think that they're pretty good questions, or I get them a lot in one variation or another, I try to include them in the live stream because I think probably more people are asking themselves that question than are reaching out to me. So just as a reminder, you can find the live stream on slackademia.com. If you go to the study guides page and you scroll to the bottom, it is a free course, Physics 8A live stream. It has all the live streams that I do with the problems that I solve, as well as the homework problems that are solved. So you can go find that there. If you want to get in touch, the easiest way to do it, if you don't use the form on the website, is to just DM me directly through Facebook. And our Facebook page is facebook.com/myslackademia. So let's start with a question that I got a lot about projectile motion this past week. It's a good question, and let me switch to this view real quick so that we can have more real estate to work. And as you can see my iPad, let me just get this green screen up real quick. There we go. All right. So let's talk about projectile motion real quick. At this point, you all know what projectile motion is, right? It is the motion of a projectile, let's say a golf ball or a cannonball, through the air with only the weight force acting on it. So now that you know what the weight force is, it kind of makes a lot more sense. And I'm going to tie that to Newton's laws actually at the same time so that we can kind of kill two birds with one stone. But we're saying that all throughout the motion here, all throughout the flight, the only force acting on this projectile is the weight force. Doesn't matter where you look, that's the only force acting on it. Now, I will say, because this is also a classic confusion, yes, there has to be a force exerted on this, if you call it a golf ball or a cannonball, let's say a golf ball, there has to be a force exerted on the golf ball to launch it at first, right? With a velocity v0 at an angle theta above the horizontal. Yes, someone had to grab a golf club and hit the golf ball. I got it. The problem begins after that happens. So yes, there was necessarily a force that set the golf ball into motion, but The problem begins once that happens and the golf ball has a velocity v0 with which it is launched. So we don't worry about forces there. Now we are going to worry about the weight force as the ball flies through the air. Okay, and the question that I got for that matter is, well, how is velocity upon impact 0? I don't understand, because isn't it the case that if the projectile hits the ground, it stops, right? Or it hits, I don't know, a wall or something. It doesn't have to hit the ground. It could strike something here, but why is velocity not 0? And it's not that velocity isn't 0, it's just 0 after the impact occurs. So let's, just to clarify this, now that you know about Newton's second law, if we let x be the horizontal and y be vertical up, f net x, first of all, well, it's going to be max by Newton's second law. But that's equal to, well, let me not do that. Let me just write that for now. Let's just write Newton's second law. Okay, f net x and f net y, respectively equal to max and may. Okay, what's f net x? Well, there is no net force in the x direction. The only force that we have is the weight force. The weight force is straight down, so it's along minus y, no component along x. So 0 is max, effectively ax is 0, and then minus mg is equal to may. And so we come to the conclusion that ax is 0 and ay is minus g. That's because I choose up to be positive. If you choose down to be positive, then you'll find ay is g. But the point is, there's no acceleration along x, and there's only gravity in the negative y direction in this case, which is what we said last week. And we said it's a property of projectile motion, because the property, or the definition rather, of projectile motion is that as the projectile flies through the air, the only force acting on it is the weight force. So you can't have a rocket that self-propels, you can't have a plane with turbines that flies, that has lift and drag and all of that. No parachute, no nothing. It's just you hit a golf ball, flies through the air, and by the way, we neglect air resistance because, well, we typically neglect air resistance in this class, and it's just that it's hard to account for. So that's why we choose to neglect it. Now, very rarely will you have to deal with air resistance, but then the whole point of the problem is to talk about air resistance. So the problem will tell you, oh, this, air resistance is non-negligible, and this is the formula for the force exerted by, for the drag force, if you want to call it that, or for the air resistance force, whatever the name is. The point is you'll be given a formula, and then there will be questions surrounding that. There will probably be quite curated questions and not that complicated, but the point is, in general, we neglect it. So if we neglect it, then there can only be the weight force like this. Fine, it is projectile motion. Ax is 0, ay is negative g. And so we said last week that, well, if ax is 0, indeed, then the speed is constant along the horizontal, which is true. So the shadow of the golf ball travels at constant speed on the grass, right? And then the y direction, well, speed or velocity is going to change because you slow down on the way up and you speed up on the way down. But velocity is never 0 anywhere, right? So let's do this. Let's just say, okay, let's call this v0x. It's the x component of v0, right? Well, it turns out, because there's no acceleration to change this x component of velocity, this x component of velocity will be the same everywhere, including at the top, because yes, here vy is 0, but vx is not, right? Remember that the x and y directions are independent from each other. So keep in mind that, keep in mind that this argument alone is sufficient to say that velocity is never 0 anywhere. The y velocity, yes, not the x velocity. And so it doesn't matter where you are, including at the point of impact, velocity is non-zero. And in general, the reason it's an impact is because velocity is not 0. After the impact, after the golf ball hits let's say the damp dirt, and makes an imprint in the dirt, then yes, the golf ball will come to a stop and will have zero velocity. But when it strikes the ground, it has velocity. That's why it makes an imprint. Okay. Now that's true for that matter anywhere throughout the flight. Now, let me just I'll draw the y component, right? Just to show that it decreases on the way up all the way to Vy is 0 up here at the top, and then it increases on the way down. So if you account for that, then even worse. There's definitely no point throughout the motion where there is a zero velocity overall. There's always a non-zero velocity throughout the flight. Same thing is true if you don't hit the ground. You don't have to have an impact here. If this is a cannonball and you strike the castle wall here, for instance, well, clearly you have x and y velocity. And that's the whole point of building a cannonball in the first place. If you have a cannonball that has zero velocity upon impact, it's a terrible cannonball. It doesn't achieve anything, but it stops right when it hits. Whereas in reality, it stops because it hits. So something to keep in mind, that there is no point throughout the motion where velocity is zero. There is a point throughout the motion where the y velocity, and the y velocity only, is zero, but that's it. Okay? So that was a good question, I thought, and now, by the way, to tie it all together, we know how to get this, right? We had to believe that at first, just on faith, that there was no acceleration along x and just negative g along y. But now we can actually derive it if we want to, because we know about Newton's second law. Okay, so then now moving forward, let's recap what we've learned so far and try to understand how Newton's laws fit into what we've learned. So let's do a quick recap here. And we've talked about position. I'm just going to write it in the x direction, but you can also, include the y direction if you need. The point is we have position. That is given by 1/2 axt squared plus v naught xt plus x naught, right? Because acceleration is constant, so then position looks like this. Then we have velocity, vx of t, which is just going to be axt plus v naught x. And then we have acceleration. I'll write it ax of t, and this is going to look a little silly, but humor me. I'm going to write it just equal to ax, by which I mean it's a constant, it's not a function of time. And to go from here to here, we said, well, it's the derivative, right? So how fast position changes with time is your velocity at any given moment. And then how fast your velocity changes with time at any given moment is your acceleration. And of course, if you wanted to go upward, you'd have to integrate your acceleration with respect to time. And then you'd have to integrate your velocity with respect to time to get position, or displacement, really. Point is, we don't have to do that. We have these formulas, right? It's just mathematically, it's interesting to understand how they're related. And that's all we had done. We had just talked about position, velocity, acceleration. We had mentioned that acceleration is constant. And at first we just did motion in one direction. But then the following week we said, well, we could do projectile motion. Projectile motion is kind of nice because, well, acceleration is constant along x, but it's 0, versus acceleration is constant along y, but it's negative g. So I get to simultaneously have motion at constant velocity in one direction and motion with varying velocity, in other words, a non-zero acceleration, in the other direction. So I get to kind of kill two birds with one stone there too. So that's kind of nice. But we were limited because, well, we just had to believe this. We had no way of deriving it. And we just had to either be given acceleration for a given problem, or be told, oh, well, the ball is, you throw it through the air and then, okay, it's free fall. So you know what acceleration is because of that. But, I mean, that does restrict our ability to solve more complicated problems or deal with more complicated situations in general. So if we could find a way to figure out what acceleration is, well, that would be nice, because perhaps not everything in life is projectile motion, and we'd like to study a crate being pulled up a ramp or something like that. So that is where Newton's laws fit in. So in particular, the one that's going to give you acceleration is Newton's second law. So I'm going to write N2L, and that is going to be, it's F net equals ma, but the truth of F net equals ma is that we typically write it along the x direction and the y direction, unless there's only one direction in the problem, but most of the time along both directions to have the component form of F net equals ma. Okay, so that is where Newton's second law fits in, right? It's going to tell you the acceleration, if there is one, for the given problem. Now, Newton's first law is similar. It's just that because the object is at rest or moving at constant speed, well, there's really no acceleration. So in other words, Newton's first law, not suggesting that it's not important, it is, and we'll see problems where we have to apply it, but we're just going to get F net x is 0 and F net y is 0. And so it fits in here because, well, it's part of Newton's laws, right? So of course we need to talk about it. But it doesn't help me get acceleration. So I'm just going to put it here for now for reference. And when we need it, we can invoke it and we can use it. But typically what it tells us is, well, we get to solve for a force, right? If the sum of the forces is 0, perhaps one force is unknown, we can solve for that. But we're not going to get acceleration out of it because there is no acceleration. There's no motion when it comes to Newton's first law. Or if there is motion, it's motion at constant speed in a straight line, right? So, no acceleration for Newton's first law. Newton's second law is a good tool to get acceleration by writing F net equals ma along x and y. And then we have Newton's third law. Okay, well, Newton's third law is a little bit of a different one. It's a statement about forces. It's force of 1 on 2 is minus force of 2 on 1. Now, careful, if I put a minus, I mean direction. So I'll put vector arrows on top of these guys so that we don't get confused. But the idea is that for any force that you can encounter in nature, there is a reaction somewhere that has the same magnitude and the opposite direction. Okay. So the typical example is that if you push on a wall, right, with a certain amount of force, let's say 100 Newton, just to pick a number. Well, that, of course, the wall feels the force of you pushing on it. That doesn't mean the wall goes anywhere or crumbles. It knows the difference between you pushing on it and not. So it'll experience 100 Newton. Now, of course, the way we say it, it's about language, really. We'll say, well, the wall pushes back on you. She's like, well, I don't know, like the wall, how can the wall push on me? That doesn't make any sense, right? So we'll say the wall pushes back on you with the same amount of force, 100 Newton, not more, not less, in the opposite direction. You're like, well, I don't get it. I don't see how the wall can push on me. It's not alive. It doesn't have arms. It can't decide to exert a force on me like I exert a force on it. All that's true. The point is, because the wall does not move, even if it did for that matter, but let's say, just to keep it simple, the wall doesn't move. Well, if you remove the wall and you continue to try to do this, you are going to move forward, maybe even fall forward, because there's nothing stopping you. Okay, well, what's stopping you here is the fact that the wall doesn't move and doesn't crumble. So, opposing you trying to push it in, there has to be something that keeps you in place, that balances you so that you don't fall forward on your face. Because if you try to push in this direction, like this, really hard and leaning into it, well, if there's nothing to stop you, you're going to fall forward. So yeah, okay, the wall's not alive. It doesn't have a conscience. It can't decide to push back on you with 100 Newton, but effectively it does. It exerts a force on you that opposes the force that you're exerting on it. And overall, Newton's third law tells you that you have an action-reaction pair. And so the idea is that any force that you can find in nature has a reaction paired with it somewhere else that comes from another object, right? And if object 1 exerts a certain force on object 2, then object 2 will exert the same amount of force on object 1 in the opposite direction. So if we recap, we know that there's three laws that are part of Newton's laws. The most common one is Newton's second law. That is the one that we are going to use the most. Followed by Newton's first law, because we'll see that there's a lot of problems that deal with either equilibrium when you're at rest or equilibrium because you're moving at constant speed in a straight line, called dynamic equilibrium. And then the one we use the least, or that we don't encounter that much, at least at first, is Newton's third law. And so that's kind of going to be true with the problems that we do today, where I want to focus on the most important ones off the bat because, you know, midterm's coming up and we need to understand Newton's laws and dynamics is the name of the chapter as much as possible, as quickly as possible. So I want to focus on the ones that really matter, which is Newton's first law and second law. But Newton's third law is going to be useful now and then, and we'll see problems where you have to argue Newton's third law to actually really solve it in the end. But the point is the following. Newton's second law is the best one to find acceleration because really it's the only one that involves acceleration. Newton's third law is useful as far as forces go, particularly if you have multiple objects that are either pushed against each other or stacked on top of each other and moving. But that helps you with F net x and or F net y. And then Newton's first law, well, yes, Newton's third law might show up in here, but Newton's first law, in the end of the day, is going to be able to pretty much let you solve for force, at least at first. Like from there, maybe you solve for something else, but it's a statement about forces canceling in the x direction and in the y direction. So what we're trying to build out is a toolkit to explain how and why objects move. And I want to know where they're going to be, whether they move or they don't move. Maybe I don't push hard enough or pull hard enough on an object to get it to move. Maybe I do, and then it moves, but maybe there's friction. Does it slow down to a stop? What happens? And so we're trying to develop these tools. The first layer was kinematics, just to explain that, well, objects can move, and let's do simple examples to understand, in and of themselves, kinematics, how these quantities are related to each other. And then add Newton's laws. That's a good addition. And then you'll see that next week we're going to do a bit of a separate topic, which is circular motion, but it's going to tie back into Newton's second law anyway. And then after that, we're going to talk about work and energy. And so can we explain how things move, maybe not from a point of view of forces and time with kinematics, but maybe from a point of view of forces and distance with the work done by a force, and how does that change the energy going in or out of the system? So we're trying to develop tools, again, to explain how and why things move and predict what they're going to do and when they're going to do what they will do. So the first new addition is talking about Newton's laws this week. Okay, so with that said, let's jump to a few problems. I actually have 3 problems for today, so we got a lot of work to do. But I tried to boil it down to 2, and I just couldn't get myself to do it. There's different things I wanted to say about all 3 of these problems, and I think all 3 of them are important. So we're just going to go through them, and we'll start with this one here. All right, so the goal here, before we even start, just to be clear, because this one tends to confuse students a little bit if I don't give some context. The goal here is to figure, and this is a very, very classic type of problem. The goal is to study 2 things. Is to say, well, okay, I have a block, and I'm going to pull it with a tension force at a certain angle, but just because I pull it does not mean that it's going to move. However, if I pull hard enough, then it will slip and move. Okay? But first I want to know how hard do I have to pull so it starts to go. And then once it is going with that force, well, how much acceleration do I get out of it given the problem? And it doesn't seem like a hard problem, and if you're careful about setting it up, it's not. But there's a few gems in there that we need to keep in mind and realize that they're important arguments that you need to make on the exam. And nobody's going to give you a free pass if you don't, and nobody's going to tell you to make them. It's expected. So let's just start with this block that has a mass of 15 kilogram. It's pulled across a rough surface with tension T at an angle 30 degrees, and we have coefficients of static friction and kinetic friction of 0.8 and 0.2. And again, this is not the goal of this, not to be a lecture, so I'm not going to, in addition to Newton's laws, go over kinetic friction and static friction. I figure I just roll it into the problem, but you need to know what those two types of friction are, when they apply, what the formulas are for each one, and so forth. So first we want to find the minimum value of the tension force T for which the block begins to slide. Okay, so this is potentially tricky. Part of what Newton's first law tells us is that objects at rest tend to remain at rest, and objects in motion tend to continue their motion. It's hard to move mass from rest. It's hard to stop mass that's moving. That's principle of inertia. And so, yes, we're saying, well, what's the minimum value of tension for which the block begins to slide? But by begins to slide, we mean is not sliding yet. All right? In other words, find T min, and then argue that any tension greater than the number we're going to find will for sure cause the block to go. But as it stands right now, we're just what's called on the verge of slipping, and that's going to be important. So let's start with a free body diagram. Okay, so we're going to have our block here. It has a mass m, so it has a weight force mg. It's resting on a surface, so there's a normal force n. There's tension at an angle of 30 degrees. So this is theta, theta is 30. And then it's not moving. So if it experiences a form of friction, it's static friction. And static friction always points opposite the direction in which I would slip. So I would slip to the right, and I don't because static friction prevents me from slipping by pointing to the left. Okay? And just to be clear, this is x and y. All right? So we're not slipping, and eventually we want to argue that we're on the verge of slipping. But for now, let's just say that we're in equilibrium. So by Newton's first law, or we just say by the equilibrium condition, it means the same thing. We have F net is 0 in the x direction and in the y direction. Okay, so this is called the equilibrium condition. Comes from Newton's first law. It is just to say that there's no net force along x. Simultaneously, there is no net force along y. Okay. What's the net force along x? Well, T is the only force that has two components, one along x, one along y. All the other forces are just along x or y. So F net x is going to be T cosine theta, because relative to theta, the x component of T is the adjacent component, minus Fs is equal to 0, and then n, careful, plus T sine theta, often forgotten, minus mg is equal to 0. Okay? Now, let's real quick do a little count of how many unknowns and how many equations. Well, how many equations is easy? I have two. Okay, how many unknowns? I don't know T. I'm trying to figure that out. And I don't know the normal, because I typically solve for the normal force. And I don't know static friction. So kind of a bummer. I only have two equations for three unknowns. So I need to deal with that. I need to include an additional equation. And I want to find the minimum value of tension for which the block begins to slide. Okay? So the point is, and this is how static friction works, there's a certain amount of static friction. Right? And you can't get more than that amount in your given problem. That's mu s times n. But up until that amount, you could pull on this block with increasing amounts of tension and still not cause it to move. There's just a breaking point at some point where you overcome the max static friction and then it slides. But there's more than one value of tension T for which the block does not move. So what we're looking for is the smallest amount of tension for which it goes. Alternatively, you could say, well, it's the same thing as the max amount of tension for which it doesn't go, however you want to phrase the question. The point is, the question will clearly tell you that you're on the verge of slipping. So we need to write something like this. So for T is equal to T min, the minimum value of tension for which this slides, the block is on the verge of slipping with Fs is equal to mu Sn. Fs is equal to mu Sn only when I am on the verge of slipping. So I can't go writing this because, cool, it's a third equation and I need that to solve without saying that I'm on the verge of slipping, because guess what? I'm going to not get credit for that. Okay, and I promise you, you will not get credit. Not even partial. Okay, if you write this, every GSI on earth is going to say, well, maybe you got lucky. I don't know why you think you can write this, but I'm not giving you the benefit of the doubt. Okay, you have to tell me that you know that it's only true on the verge of slipping. Okay, so as soon as I see that formula, I expect to see on the verge of slipping. They go together, and that I need that to justify being able to write this. Now, if I do, and then I can then rather change my equations or update my equations and say, well, now I have three equations, right? And I can just do this. I can just lump this into the first one. So now my equation is going to be what? It's going to be T min cosine of theta minus Fs, well, I'll just write mu Sn. That's equal to 0. And then N plus T min sine of theta minus mg is equal to 0. Okay, but now I'm good because I only have two unknowns, right? I don't know T min, I'm solving for it. I still don't know N, but Fs is mu Sn, so I don't have Fs to solve for anymore. I know what it is. Okay, so then we can solve this thing. Now, typically the second equation is the equation that gives you the normal force. You always solve for the normal force. And please, dear pre-meds, do not memorize that the normal force is equal to mg. It is false half the time. Okay, which is enough for it to be false all the time. So in other words, you cannot state that n is equal to mg and have it be a true statement. N is equal to mg sometimes. When you have nice simple problems, that's true. In general, just solve for the normal. And it is whatever it is, right? Just whatever your equations tell you, that's what the normal force is equal to. Okay. And so then up here, we're going to have T min cosine theta minus mu Sn is equal to 0. Okay, well, now I know what n is, so I can plug it into here. And what do I get? I get T min cosine of theta minus mu s mg minus T min sine of theta is equal to 0. Just plugged in n. What am I solving for? I'm solving for T min. And T min shows up more than once. So if I have an equation where a variable shows up more than once, I have to group the terms together, then factor out, divide. Okay, so I'm going to get T min cosine theta. Minus is plus T min, well, plus mu s. I should do it this way. T min sine of theta is equal to this term minus mu s mg is going to go to the other side. So add mu s mg to both sides, you get this. Okay, and then we can factor out T min and divide. So I'm going to get T min times cosine of theta plus mu s sine theta is equal to mu s mg, and then all I have to do is divide. So T min is mu s mg divided by cosine of theta plus mu s sine of theta. Okay. Now, again, just as a reminder, it's very hard to see that what we need to do is go from here all the way down to the answer for T-min. It's also very hard to guess what T-min is going to look like. I don't suggest that you try. Point is, all I did is write things that are true. It is true that this thing is at rest. It is true that if I want T-min, I'm going to be on the verge of slipping, so this has to be true as well. If I combine everything, I should get the answer. Especially, I can check. I have as many unknowns as equations, so then I know I can solve mathematically. I just have to trust that by starting with writing things that are true, and then by combining them, I will get the answer. It's a little weird because we don't know what the answer is going to look like necessarily. Most of the time we don't. And it's not a very, it's a thought pattern where, or a thought process where it kind of seems like we're in the dark the whole way. And we're just like kind of following along and something's going to come out and we'll see what it is. Which is what it is. That is exactly how you do it. And the beauty is that if your equations reflect this specific problem, well, if you have a slightly different problem, all you have to do is adjust your equations. And then maybe you get a different type of answer, but you've solved a different problem, right? So rote memorization really doesn't work for this. I strongly recommend that you never try to rote memorize solutions to problems. You can rote memorize however you want to memorize lecture notes and all the formulas and all those derivations, because that's your baseline. If you don't have that, you can't think about a problem. But as you can tell here, we just, followed what the equations told us and got an answer. So that's T-min. We can compute T-min, by the way. So T-min is going to be mu s. Now mu s is 0.8. It's 15 kilograms. G is 9.8. Cosine of 30 is the angle plus 0.8 sine 30. And that's going to be approximately 92.9 Newton. Okay. Super classic setup and type of question. So, what we're saying is that, and this is worth mentioning, for 92.9 Newton, the block begins to slide. Well, not really. The block is on the verge of slipping. But for 92.9 plus 0.00000001 Newton, then the block goes. Okay. And so since writing 92.9000001 is a little ridiculous, especially since I could keep going with the zeros, we just say, you know what, the answer is 92.9 Newton. For that amount of tension, the block begins to slide, even though we said it's not sliding yet. Right? The point is, I just want that number, and the answer is anything greater than that, for sure the block goes. I just want to know where the threshold is, basically. So, that solves T-min. Question 2 then says, assuming that tension is 200 Newton, what is the acceleration of the block? Okay, well, first of all, 200 is greater than this, so for sure the block goes, and there's an acceleration. If I had been told, assuming tension is 80 Newton, what's the acceleration? The answer is the acceleration is 0. I haven't overcome static friction. But okay, now I do overcome static friction, and I want to find the acceleration of the block. So my block is now moving. Let's draw the free body diagram. Under the same tension, at the same angle, so this is tension T, at an angle theta of 30, there's a normal force, there's a weight force, that hasn't changed. And now, because we're moving, it's no longer static friction, but kinetic friction. And kinetic friction points opposite the direction in which you're moving. So pulling the block to the right would cause it to slide to the right. And if it does slide to the right, then kinetic friction points to the left. And so now, because it's moving, I can no longer claim the equilibrium condition, but I can write Newton's second law and solve for acceleration. In fact, there could be a third question. Take that acceleration and let's go do kinematics. We stopped the problem here because the point is to practice Newton's laws, but you can see already how it's going to tie into kinematics later. So let's go ahead and write Newton's second law. So I write it N2L, that's between you and I to save some time. On your exam, please write by Newton's second law. Even better, if you want to be super anal about it, by Newton's second law applied to the mass M. But don't be surprised if you get points docked if you write Newton's second law, the formulas, without prior saying by Newton's second law. Like some graders are really specific about that. That's just how they're taught in their country. That, most countries outside the US require a lot more explaining of why you get to write equations. Right? We just kind of like, yeah, whatever, you wrote the equation, you got the answer. But anyway, so N2L is between you and I so that we know what we're talking about on your exam in full English by Newton's second law. Okay, F net x is equal to max. I'm just including this step because we're getting to know Newton's second law. Right? This is kind of silly. You could just straight up write what F net x is, what F net y is, and set it equal to max and may. But I'm just doing this to get into our head that this is what we're trying to do. Okay, so what is F net x? Well, F net x is going to be t cosine theta, and that's the x component of t, minus this time kinetic friction Fk is equal to max. And in the y direction, n, careful, plus t sine theta, don't forget that, minus mg is equal to may. Okay, and we want the acceleration of this block. Now, we can do one better than this, but again, this is on you. You have to explain. I'm going to argue that ay is necessarily 0 because this block is going to travel from left to right horizontally. If it does not move up or down, there will be no velocity up or down, and therefore there can be no acceleration up or down, right? So ay is 0 because the motion is solely along x, or the block only moves in the x direction, however you want to say it. The point is you have to explain why that's true. Okay, because we know you students, when you don't like something, you tend to set it equal to 0. Like, well, okay, yeah, you got rid of it, but if you can't explain why and it's not legit, then it doesn't count. So this is legit though. There is no motion in the y direction, so there's no acceleration. Okay, then my first equation turns into t cosine theta minus mu kn is equal to max. And the beauty of kinetic friction is that it is always mu kn. I don't have to explain. Static friction equal to mu sn, that's not always true. I have to be on the verge of slipping. But kinetic friction is always mu kn. Okay, so then n, second equation, is going to give me the normal, which again is going to be mg minus t sine theta. So I can now take n and I can plug it into here and solve for the acceleration. So I'm going to get t cosine theta minus mu k mg minus t sine of theta is equal to max. Now, the reality is all you have to do is divide by m, and then you get ax. You might find people that will insist upon factoring. That's just force of habit. So they would write t cosine theta plus mu k sine theta minus mu k mg is equal to max. But it doesn't really matter. You didn't have to go that far. Ax is just going to be whatever you found divided by m. So t cosine theta plus mu k sine theta minus mu k mg divided by m. And we know all the values necessary, so we can just go ahead and plug them in. Right? And so ax is going to be equal to t is 200 cosine of 30 plus 0.2 sine of 30 minus 0.2 times 15 times 9.8 divided by 15 Let me make a little bit of room here so that we can fit it all in one line. We get AX is approximately 10.9 meters per second squared. Don't forget the units. All right, that is your acceleration. So hopefully not too bad. Again, once you've done this a couple times, it'll be a lot easier, but point is, this is a very, very classic exam question. Start at rest, static friction, verge slipping, boom, boom, then, okay, now the block goes, what's the acceleration? We could add some kinematic questions to follow up on that, but the truth is, this is a good problem just to get our feet wet and talk about Newton's laws. Okay, so that was the first problem I wanted to do today. And I wanted to do it because, again, it's a classic, and it tells us, you know, how to first apply Newton's first law, Fn is 0, then Newton's second law, okay? Then I'm going to do another one, which is going to be similar, but that's going to deal with an ideal string, because we don't know what that is, or we haven't talked about it yet anyway. We're going to solve for acceleration, but there's going to be two objects moving, so how do you deal with that? Plus, they're going to be on an incline. How do you deal with that? Okay, so this one's an old exam problem, super classic. One form or the other. You could make it harder. You could pull it down, or you could pull at an angle, or whatever the case may be. But it solves all the same at the end of the day. You're just going to try to find the acceleration of these things. Okay. So we have a block of mass 4 kilogram and another one of 8 kilogram joined together by a rope. All ropes are ideal in Physics 8A. They're on an inclined plane, 20 degrees above the horizontal. We know the amount of force that's pulling the 8 kilogram block. We know the direction, and we know the acceleration. So my bad, we're not solving for acceleration, although it's a classic question. We're solving for coefficient of kinetic friction, my bad, and then the tension in the rope. But, okay, the point is, actually this is why I chose this problem. The point is, I usually use Newton's second law to solve for acceleration. That's very common. But I don't have to. I mean, I can solve for anything that shows up in Newton's second law, right? And if the coefficient of kinetic friction, mu k, shows up in there, and I know everything else, okay, then I can solve for mu k. Why not? So that's what we're going to do. And we're going to learn how to deal with a block on an incline when it comes to the weight force. And this is going to be super important. I'm actually going to do it right here so that we don't have to stop what we're doing later to understand why what I wrote showed up. Okay, so I'm going to pick one of the two blocks. It doesn't matter which one. Let's just call it a mass M. And the weight force points straight down. Right? And this is an angle here, theta. Okay. Now, the first thing to note before we even do that is that when it comes to motion on an incline, or just even motion in general, a good rule of thumb is to pick one of the axes in the direction of acceleration. So the direction of acceleration is parallel to the incline here. So I would be very tempted to choose x to be up the incline, and then y is going to be perpendicular to the incline. That's going to be a lot easier to write forces and acceleration than if I choose this. Now, can I choose this? Yes, I can. Will I get the same answer? Yeah, the intermediate steps are going to look different, but I will get the same answer. But this is like sad face, because most of the forces acting on these blocks are either going to be parallel to the surface here or perpendicular to the surface. The only one that's not going to be is the weight force. But the weight force is nice. It's always straight down. So if it's always straight down, it will always behave the same way for any incline that I encounter in the future. So with that said, I am interested in two directions, right? Parallel to the incline and perpendicular to the incline. Okay, so let me make this a dotted line. This is the y direction. Okay, this is the x direction. Let's zoom in real quick. Okay, so this is our weight force. Weight force is two components. It has a component along x that points down, and it has a component along y that points down into the incline, if you will. Now, this component is what slows you down on the way up. This component is what keeps you in contact with the incline, with the ramp. Right? You don't crash through the ramp. You don't lose contact with the ramp. It just maintains the contact between the block and the ramp as the block slides up. Okay. Now, what is this angle here? That's the interesting question. This triangle is a right triangle because MG points straight down, which means that this angle here is 90 degrees, which means that this angle here is 90 minus theta. But guess what? This angle here is also 90 between x and y, which means that we're left with an angle here that is equal to theta. Okay? You have to be able to do this for your own sake. Now, it means that the y component now is the component adjacent to mg relative to theta. In other words, that this is mg cosine theta in length. Whereas up here, this guy here is going to be mg sine theta. I mean, you can think of it as this component here is this guy here. It's the component opposite theta relative to mg. So it's mg sine theta. Which means that the x component is, in fact, minus mg sine theta. Seems weird because usually we have cosine for the x component. And the y component is minus mg cosine theta. Seems weird because usually we have sine for the y component. Okay? But that's only true because usually we define our angles between the vector and the x or y, the x-axis. Sorry, let me say that again. We typically define the angle to be the angle between the vector in question and the x-axis. That's why cosine theta shows up in x, sine theta shows up in y component. But here we have theta defined relative to y. So it flips the cosine and the sine, if you will. Okay, but this, I mean, if you were going to memorize something about components of the weight force, I would memorize this. Or at least I would be able to re-derive it on the spot, because there is no way on God's green earth that you're not going to get an incline on one of the exams. When I used to teach, I would bet with my students that if there was no incline on midterm 1 or midterm 2, either one, I would take all 24 of them out to the French Laundry, which of course I had no means to afford that as a grad student, and well, never had to because I was always right, and that's why I made the bet. So my point is, you have to know how to deal with inclines on the weight force. Okay. All right, so I want to do that first. That's just kind of to understand why I'm going to write the components I'm going to write when it comes to Newton's second law. Okay. So I'm going to put this, I'm going to make a copy of this. I'm just going to put it here in the corner to see later, right? Or to refer to as we go, rather. And we are going to draw the free body diagram of each one of these blocks. Okay, 2 blocks means 2 free body diagrams, okay? So I'll start with the one here. I will call this one M2. I will call this one M1, just so we can keep track. And so, in fact, no, sorry. I mean, it doesn't matter, but because I said I'm starting with this one, I'm going to call it M1. All right. So what are the forces acting on M1? Well, M1 has a mass, so it necessarily has a weight force, M1G. It's resting on, well, it's sliding up this incline, so it's in contact with the incline. So the normal force will be perpendicular to the incline, N1. Then it is being pulled by the applied force F applied. And there's 2 other forces. Strings can only pull, so M1 gets pulled down with a tension called T1. And there's friction on the incline. Doesn't have to be, but in this case there is. And so friction points opposite the direction in which the block slides. The block slides up this way. Kinetic friction, because the block is sliding, points down. I got to call it FK1 because I'm going to have to discriminate with block number 2 in a second. Okay? So that's block 1, M1. What about block 2 down here? Well, M2 has a weight force, a normal force, N2, perpendicular to the surface. Strings can only pull, so it gets pulled with a tension that I'm going to call T2, for now anyway. And then there's kinetic friction going opposite the direction in which M2 slides, and therefore FK2 points down the incline. Okay? All right, so then get rid of this thing. What do I know? Well, I know a lot of different things. I know acceleration, so I'm going to write F net equals ma. I'm going to try to solve from UK. And there's something to say about the fact that we have an ideal rope. Okay, so I'll start with that. Ideal rope means that T1 is T2. The tension is the same everywhere in an ideal rope. That's just a property of ideal ropes. Okay, so T1 is T2, right? And ropes can only pull, so it pulls down on M1 and up on M2. Then we have what's called an acceleration constraint. Now this is just, this is physicists making up words so that they understand what they're saying, but you don't. If you don't think that it's a thing, go read a scientific paper. See the words that they use, just so that you don't understand what's going on. Acceleration constraint just means these two blocks move together. They're connected by a string that never goes slack. So guess what? If this one goes up with 1 meter per second squared, this one too. There's no choice. They have to. They move together, right? So that's all it means. You could write in English, the blocks have the same acceleration because they move together if you want. Nobody cares. There's just the short way to say it is that there's an acceleration constraint. The acceleration constraint is that A1 is equal to A2. Now, truth is, I'll just call it A because, I don't need to discriminate between the accelerations if they're the same. Okay? So, and I know that acceleration is 2 meters per second squared in this case. So then I'm going to write Newton's second law applied to this thing. Right? As a reminder, x is positive up the incline, y is positive perpendicular to the incline. So Newton's second law is going to give me the following. So first of all, for M1. All right, so F net in the x direction is going to be F applied, points up the incline, minus M1g sine of theta, which is the x component of M1g, like we said before, minus T1, minus FK1, but FK1 is mu k N1. And that's all equal to M1AX. And then N1 minus M1g cosine theta, that's the y component of M1g, is equal to M1AY. Okay, now we can do a little bit better than that. We can say that AX is actually A1, and we can also say that AY is 0, because there is no motion along Y. And you might say, well, that's weird. Isn't Y up? Doesn't the block move up as it slides up the incline? And I would say, yeah, it does, but that's not what Y is. We just redefined Y to be perpendicular to the incline. Now, if the block slides along the incline, it does not move in the Y direction. So there's no acceleration in that direction. Same as before in the problem where we said if the block moves horizontally, there's no motion in the Y direction. In that case, Y was positive up. All right. So that's for M1, okay? And then we're going to do the same thing for M2. I'm actually going to do it up here so that we can see the free body diagram as we write the equations, and then I'll move the equations down. F net x is going to be T2 minus M2g sine theta minus fk2, which is really mu k and 2, is equal to m2 ax, and then n2 minus m2g cosine theta is m2 ay. Well, same thing. Ax here is really a2, right? And then ay, for the same reasons as below, is 0 because no motion along y. Okay. All right, so we have our equations, right? By the way, the second equation for each one is going to give us n1 and n2, right? So we can just, let's just, between you and I, right? I mean, you would be able to see this, but just so that you can follow what I'm about to do, right, I'm going to plug n1 and n2 into the x equation for each block, right? And then eventually I'm going to argue that t1 is t2. Okay, so let me do the following. Let me rewrite this first equation as t1 is equal to, and it's going to be equal to f applied minus m1g sine theta minus mu k, n1 is m1g cosine theta, minus m1a1, but a1 is just a. We said that earlier. And that's it. That's equal to t1. Okay, and for t2, I'm going to have t2 is m2a2, but a2 is a, plus m2g sine theta, plus mu k, n2, which is m2g, cosine of theta. Right? That's t1 and t2. But the easiest way to solve is to say that t1 is equal to t2. Now, typically you'd be solving for acceleration for this type of question, but okay, sure, if you want to give me acceleration instead, then I can solve for whatever else. Let's call it mu k. All right, so if t1 is equal to t2, it means that this whole thing here is equal to this whole thing here. All right, and so then we are solving for mu k. Let's group the terms that have mu k in them, which are these two terms. I'm going to throw this one to the right, and everything here on the right I'm going to throw to the left. So I'm going to get f applied minus m1g sine theta minus m1a minus m2a minus m2g sine theta is equal to mu k m1 g cosine theta plus mu k m2g cosine theta. Okay. All right, and oh my, do we have some factoring to do here? So you don't have to, but this is what you're going to see in an answer key because we can't help ourselves, right? So it's going to be minus m1 plus m2a minus m1 plus m2 g sine theta, which means we can factor one more time even. And this is going to be mu kg cosine of theta times m1 plus m2. Okay. So we can just solve for mu k. Right, just going to divide by g cosine theta m1 plus m2. So mu k is going to be equal to, all right, now the numerator is going to be f applied, Again, you don't have to do this, but if you see it, you can do one better. It's minus m1 plus m2 a plus g sine theta divided by g cosine theta m1 plus m2. Okay, so we can compute this. Mu k is equal to 130 minus 8 plus 4, 2 plus 9.8 sine of 20 divided by 9.8 cosine of 20, 8 plus 4. And that's going to be approximately 0.6, and no units because it's mu k, it's a coefficient of friction, which is really a ratio of two forces, so it has no units. All right. So that takes care of finding mu k. Not too bad. Yeah, not too bad. So now that we have that, we can then go address the other question. Now, the other question, if you recall, was what is the tension in the rope connecting the blocks? Now, I see students get stuck there at the question because you're like, well, what else do I write? You know, I've written all this. Did I forget something? Do I need a new equation to find tension? No, you don't. You've done all the work, yeah? Here you go. Pick the one you want. T1 is equal to T2 anyway. So you can pick the one you want. I mean, if it were up to me, I would probably pick this one because it's a little simpler. But, you know, whatever. Like, you can pick that one or another and say, okay, well, the tension, T1 is T2. So since T1 is equal to T2, we have T1 equals T2 equals this thing. It's going to be equal to 4 times 2 plus 4 times 9.8 sine 20 plus 0.6 times 4 times 9.8 cosine 20, which is going to be roughly 47 Newton. There we go. So, you know, very easy to get tension once you've done all that work before. It's just a matter of plugging back in. So finding the first piece, like in this case mu k, typically acceleration, that's the hardest piece, and then everything else kind of follows from there. So these two problems were good applications of Newton's first law and Newton's second law. It also helped us touch on what happens if you have multiple objects. So what happens if you have two blocks connected with an ideal string. And those are kind of like satellite topics or peripheral topics, you know. Okay, Newton's laws are the bulk of it, but an ideal string means tension is the same everywhere in that piece of string. Blocks move together means there's an acceleration constraint. So that's an ideal string plus the notion of multiple objects having to move as one, in a sense. There's a third one, which is why I couldn't get myself to cut one of the three problems, which is the ideal pulley, which we haven't talked about. Now, the ideal pulley is such a classic that we need to talk about it for sure, because there's a good chance there's going to be an ideal pulley on midterm 1. Right? And if not, you know, don't worry, it gets worse. On midterm 2, there might be a pulley, it just might not be ideal. So, to be sure that we've covered all our bases, let's go over the at-one machine, which is unbelievably classic. There's no way you don't see this problem either in lecture, discussion, both, office hours, whatever. It's extremely common, and it's extremely common to have a variation of this on exams. Now, the idea is that you have two masses, M1 and M2, connected via an ideal string, so you know how to deal with that, wrapped over an ideal pulley, and then if you let them go, one goes up, the other goes down. That's it. It's that simple. The question is, of course, what does it mean to have an ideal pulley? And so let's start by dealing with that, because it's just you need to know what to write in the same way that, you know, for an ideal string we knew what to write. So in fact, let's even start with the strings. Strings can only pull.
So string is going to pull with tension T1 on M1. But if I look at how it pulls on the pulley, it's going to pull with an amount of tension, I'm going to call it T3, because then on the left-hand side I want to make this T2, the amount with which it pulls on M2, but it's going to pull on the pulley with an amount of tension, let's call it T4. Now I have an ideal string. Now the ideal string tells me that in my piece of string the tension is the same everywhere. I have to be a little bit careful with that when it comes to pulleys because I actually need to treat these two strings as if they were separate. Right? It's just, of course, it's one string wrapped over the pulley, but while I'm certain that T1 is T3, in other words, that the tension in this piece of string is everywhere the same, and that T2 is T4, in other words, that the tension everywhere in this piece of string is the same, I'm not convinced that T3 is T4. Now, it turns out it is, and we can't explain it until later, but by definition of an ideal pulley, the tension on either side of the pulley is the same. Now, that comes from the fact that an ideal pulley has no friction on the axle and no mass, meaning that the effort required to rotate the pulley is zero. In other words, T3 can be equal to T4 and you can still get the pulley to rotate, which of course is a simplification. In fact, if you wanted to go this way, you would need T3 to be bigger than, T4, to be bigger than T3, not equal. But if you have an ideal pulley, it simplifies things and you can say that the tension on either side of the pulley is the same. All right, so T3 is equal to T4. Okay, so now we know how to deal with ideal strings. Well, we already knew that. We now know what to write for an ideal pulley. Tension on either side is the same. We are going to have an acceleration constraint here. It's not as obvious as the previous one, but you know, M2 moves down because M1 moves up. So I have an acceleration constraint, and I want to write that in magnitude, M1 and M2 are going to experience the same acceleration. Okay, because if M2 falls 3 feet, M1 rises 3 feet. Yeah? So, they will have the same acceleration in magnitude. In other words, A1 is A2. Let's just call it A. A1 will be upward, and A2 will be downward. Now, careful with that one, because in the previous problem, both blocks were being pulled up the incline, so cool. Obviously, A1 and A2 are the same in sign, right? Well, here I mean to say that A1 and A2 are the same in sign because I'm assuming A1's a positive number, A2 is a positive number. So in magnitude, they're the same, but there's a direction that's flipped. So then we go back to the other rule that we mentioned, which is that you typically try to pick an axis that is in the direction of acceleration. It's just good practice. I have two objects, so I'm going to choose Y1 to point up because A1 points up, and Y2 to point down because A2 points down. Now you might say, hey, can you do that? Can you have different axes for different objects? And yes, I can, right? It doesn't matter, right? The point of the axis, whether there's one or more than one, is that, let's say for M1 you use Y1. Well, once you've written Newton's second law, and you have the relationship between the forces, the mass, and the acceleration, then that relationship, that equation, in a sense forgets what Y1 is. It doesn't matter. The equation exists in and of itself, and you can use it. Same thing with M2. So you can use the same axis for both, or you can use different axes for both. What matters is that the relationship for each one be written properly, and then you can go ahead and solve. So you see what I mean? Right, so let's just draw the missing two forces for each one of these. For M1, we're missing the weight force M1G, and for M2, we're missing the weight force M2G. All right, and then by Newton's second law, okay, starting with M1, well, F net Y is equal to M1 AY, which is A1. Okay, up is positive, so that's T1 minus M1G is equal to M1 A1. And this is positive because, yes, A1 is up and up is positive. What about M2? Okay, well, for M2, down is positive. So it's going to be M2G minus T2 is equal to, now careful, M2A2, because down's positive, A2 is down, so this is positive. And then we can solve. T1 is equal to T2 because, well, T1 equals T3, T3 equals T4, T4 equals T2. All these tensions are the same because of the combination of the ideal string and the ideal pulley. Right. So I can do one better. I can say, well, I don't need A1 and A2. I can just call the acceleration A in both cases because it's the same. And so now that I've written these equations, it doesn't matter that y1 was up, y2 was down, right? It just matters that these quantities have a certain relationship between them that I properly wrote. I can then use these equations and solve. It's no longer tied to y1 and y2. Which is why I can use one axis per object if I want to. All right, so let's solve. What's the best way to solve? Well, we're going to write T1 is M1A plus M1G. And then here we're going to write that T2 is M2G minus M2A. And if we recall that T1 is equal to T2, then we can say that M1A plus M1G is equal to M2G minus M2A, and I'm solving for A. Okay, so I'm going to put M1A and M2A on the same side. And I'm going to subtract M1G on both sides. That's going to give me A factored out. M1 plus M2 is equal to M2 minus M1G. A is going to be equal to M2 minus M1 divided by M1 plus M2 times G, which is 6 minus 4 divided by 6 plus 4 times 9.8. Well, that's 2 over 10. So 9.8 over 10 is 0.98 times 2 is 1.96 meter per second square. All right. So that's the acceleration. And then if we want to find, what do we want to find? We want to find the tension in between, or the tension in each rope, rather. Right, find the tension in the string. Well, same as before, I don't have to write anything new. I've written everything that I can. I can use this or I can use this, it doesn't matter. Right, I'm going to get the same answer. So let's call it, T1. So T2 is equal to T1 is equal to this, right? And so M1 is 4 times 1.96 plus 4 times 9.8. Right, and so that's, actually, I didn't compute that. Let me compute it real quick. And that's going to be 4 times 1.96 plus 4 times 9.8. That is 47. All right, which, now that I say that, I should go check this. This is not 47. There's no way. I was getting my wires crossed on that one, so let me check this. 4 plus 4, 9.8 times sine of 20 plus 0.6 times 4 times 9.8 times cosine of 20. This is 43.5. All right. So, anyway, those are the 3 problems I wanted to do today. Hopefully it's clear why I wanted to do them. I know we did not talk about Newton's third law. That's kind of on purpose. Newton's third law, we are going to need it. It will be a lot more obvious why once we do more complicated problems. So I'm not suggesting table Newton's third law for now. You definitely, if you see it in discussion and you want to start thinking about it and you see it being incorporated into problems, that's good. It's just the main equations that we tend to write are Newton's first law, which is equilibrium, and Newton's second law, F net equals ma, along x and y. And yeah, Newton's third law, again, we'll see later on how that fits in. But what we've done is we've now tried to explain why objects move or why they don't move, right? And so is the object at rest given the forces, or does it move given the forces? If it does move, what's the acceleration? And note that I didn't incorporate any kinematics into this batch of problems, right? Well, all we did, if we go back, is solve for acceleration first and then maybe tension. So deal with accelerations and forces. That was the main focus. We did not then say, oh, well, if you know the acceleration, how fast is the object moving after 4 seconds? Like we could, and that would be stuff we did the last 2 weeks. So, the additional layer or the additional, the upgrade to our toolkit is now that we have Newton's laws, we can determine if something moves or not, and if it does, we can find the acceleration. We can tie it back to kinematics. Next week, we're going to do a bit of a detour into circular motion, which we do it now because it ties into Newton's second law, and it allows us to talk about it once first, right now, and then later, when it's going to show up again-ish in the form of solid rotation. So at least we get to talk about it now and sort of introduce the idea, and it ties in nicely to Newton's second law, but it is kind of a chapter in and of itself, like it's kind of standalone. But the week after that, we're going to do work and energy, which is going to be another upgrade to our toolkit, where we're going to try to figure out if I have a certain force over a certain distance, maybe I don't care how much time went by, I just can use that to figure out how fast I end up going, because it seems that for a given force and a given distance, there should only be one speed at the end that I achieve. So that will be, again, we're upgrading as we go, and we're going to spend the whole time all the way up to almost midterm 2 developing the tools that we need to describe how things move, and we're going to study things that get more complicated, such as maybe collisions and what happens during a collision and how do I account for it and things like that. But it's all based on Newton's laws for the most part, actually overwhelmingly, except kinematics. And therefore, we're building as we go, which means that try to not fall behind, because what you don't want to do is, beginning of October, whenever midterm 1 is, start diving into all of this and piling it all up, kind of cramming, because I'm not saying you can't do it. I'm just saying it will help you have more clarity if you, as you go, you progress through these, as opposed to stacking it all into a 3-day review when the midterm comes around. Now, I know that's easier said than done, but I would encourage you to stay current with the material if you can. And so that takes care of this live stream for this week. I'll be back next Tuesday, so pretty soon, to do circular motion and talk about that. In the meantime, let me know if you have any questions. As always, thanks for watching, and if you need help with Physics 8A, feel free to reach out. Happy to help you and set you up with what you need. Take care.